If you want to keep up to date and get notified when we release new videos, click on like and subscribe. This helps us keep the channel going and lets us know that you're enjoying our content. Ever wondered what happens if you drop your keys into a black hole? Well, consider them gone forever. Black holes, the universe's most enigmatic and elusive phenomena, have always aroused curiosity and intrigue. Imagine them as cosmic vacuum cleaners, sucking in everything that comes too close, from light to your unfortunate keys. The structure of a black hole is deceptively simple, especially the non-rotating ones. At its heart lies a singularity, a mysterious point where our understanding of physics breaks down. Surrounding this singularity is the event horizon, the point of no return. If your lovable robot companion, your plastic pal who's fun to be with, ventures past this threshold, it's goodbye forever. The phrase, "nothing can escape," holds its truest meaning here. Now let's consider our own bodies. Our diet, our lifestyle, everything we consume leaves a trace. A medical professional with the right tests can determine what you've been eating. The question we aim to explore today is, does the same principle apply to black holes? Can we, through their gravitational field, discern what they have consumed? In the realm of general relativity, a black hole is characterized by three parameters: its mass, electric charge, and angular momentum. Usually mass is the most significant parameter, but to reconstruct a fully functioning robot, one would need much more than just these three parameters. This brings us to a paradox. Black holes, the epitome of cosmic simplicity, seemingly defy one of the fundamental principles of physics, the second law of thermodynamics. This law states that the universe's disorder or entropy will always increase over time. Yet when you throw your keys or your robot into a black hole, they vanish, seemingly reducing the universe's entropy. This makes black holes seem like a thermodynamic anomaly, a zero entropy system that lasts forever. But as with most things in the universe, black holes might be more complex than they first appear, particularly when it comes to understanding what happens to our robot once it crosses the event horizon. So in a nutshell, once something enters a black hole, it never comes out. But what exactly happens to it inside? Black holes might seem simple, but there's more to them than meets the eye. On the surface, they're just celestial objects with such strong gravitational forces that nothing, not even light, can escape their grasp. But let's delve a little deeper, shall we? A black hole is largely defined by three parameters: its mass, electric charge, and angular momentum. The mass of a black hole is what gives it its gravitational pull. You can think of it as the black hole's weight, if you will. The electric charge, on the other hand, is usually negligible because black holes tend to swallow up equal amounts of positively and negatively charged matter. Lastly, the angular momentum is related to the black hole's spin. Yes, you heard right, black holes can spin, much like our own planet. Now, these three parameters are all well and good, but they don't account for everything. Think of it this way: if you were to throw a robot into a black hole, these three parameters wouldn't be enough to put that robot back together. It's a bit like trying to build a car with only the weight, color, and speed. You're missing a whole lot of details, aren't you? And here's where things get even more interesting. Black holes seem to break the rules of physics. Specifically, they appear to violate the second law of thermodynamics. This law states that the total entropy, or disorder, of an isolated system can only increase over time. But when you throw something into a black hole, its entropy seems to disappear. It's as if you've cleaned up a messy room by simply tossing everything into an invisible closet. So, black holes seem to break the rules, don't they? They swallow entropy and appear to have none of their own. But, as we'll see in the next scene, things aren't quite so simple. Because when it comes to black holes, there's always more than meets the eye. But hold on, black holes aren't as simple as they seem. They may appear to be universal delete buttons, but there's a lot more going on beneath the surface. Let's dive into the heart of the matter, shall we? We've already established that black holes feel like a direct challenge to the second law of thermodynamics, which states that the universe's disorder, or entropy, always increases over time. And yet, black holes seem to be the epitome of order. Everything that enters a black hole is stripped to its most basic properties: mass, electric charge, and spin. All the other information, all the entropy, just vanishes. Or does it? This is where the concept of black hole information comes into play. This principle suggests that all the information about what falls into a black hole is somehow preserved, not lost. It's as if the black hole takes a detailed snapshot of everything it swallows, storing it away for, well, we're not quite sure what for. It's a bit like a cosmic recycling program. The universe doesn't like to waste information. Even in a black hole where everything seems to disappear, the information is kept. It's just transformed, reshaped, but never truly lost, and this concept has profound implications for our understanding of black holes. It suggests that black holes aren't the ultimate destroyers we once thought they were. Instead, black holes could be more like cosmic librarians, meticulously cataloging everything they consume. So what does this mean for our robot friend who we sent into the black hole? Well, while we may never see him again, his information, his essence, if you will, lives on. The black hole has remembered him in its own unique way. This is the complexity of black holes, the fascinating interplay between entropy, information, and our understanding of the universe. It shows us that black holes are not just simple one-way tickets to oblivion. They're intricate, dynamic, and full of surprises. So, black holes might be more memoryful than we initially thought. They're not just cosmic vacuum cleaners. They're cosmic record keepers, in a sense, holding on to the universe's secrets in ways we're only just beginning to understand. Remember our question about whether black holes remember what they consume? Well, let's dive into that. The simplistic characteristics of black holes, their mass, electric charge, and angular momentum, are affected by the things they consume. When a black hole devours an object, the object's properties, like its mass and charge, are integrated into the black hole's parameters. So in a sense, black holes remember what they swallow, but not in the way we remember our last meal. Now let's consider this in the context of the laws of physics. The second law of thermodynamics, for instance, is a fundamental principle that states entropy always increases over time. When an object is swallowed by a black hole, it might seem like we're violating this law because we're essentially erasing the object's entropy. But here's the twist. Black holes themselves possess entropy. Yes, you heard that right. In the 70s, physicist Jacob Bekenstein proposed that a black hole's entropy is proportional to the area of its event horizon, the point of no return. This was a revolutionary idea at the time, and it led to the concept of black hole thermodynamics. So, when your keys or our proverbial robot fall into a black hole, they're not violating the second law of thermodynamics. Instead, the entropy of the consumed object gets added to the black hole's own entropy. The object's information isn't lost, it's encoded into the black hole's event horizon. This concept, known as the holographic principle, suggests that all the information about what's inside a black hole is stored on its two-dimensional surface. It's like the universe's most efficient storage system, albeit one we can't access once something crosses the event horizon. So, while your keys might be gone forever if you drop them into a black hole, the black hole remembers them in its own unique way. So, are black holes as bad as they seem? We've journeyed far today, traversing the cosmic abyss and venturing into the heart of darkness, the black hole itself. We've explored the simplicity and complexity of these celestial phenomena and pondered on the memory of black holes. Remember, a black hole, especially the non-rotating ones, are fundamentally simple. Yet they hold a profound mystery in their simplicity. With an unknown singularity at the center and a point of no return lurking ominously, black holes are the epitome of cosmic enigma. And yet they are not as bad as they seem. Think of it this way: when you consume food, it becomes a part of you, shaping you in a way. Similarly, whatever falls into a black hole becomes a part of its character. But here's the catch. While your doctor can tell what you've been eating by examining your blood and other vital signs, you can't do the same with a black hole. The only parameters that can describe a black hole in terms of general relativity are its mass, electric charge, and angular momentum. Yet, the universe's randomness makes the event horizons of black holes incredibly fascinating places. Perhaps one day, we might even find a way to retrieve the information lost in a black hole. But that's a topic for another day. For now, we are left with more questions than answers. Are we overthinking the complexity of black holes? Are we overstating their simplicity? Should we take a less speculative approach in studying these phenomena and focus more on practical physics? Or perhaps some things are best left unexplained, their mystery maintained, their secrets kept hidden in the fabric of the cosmos. What do you think? Are we overthinking black holes, or is there more to them than meets the eye? Share your thoughts in the comments below. If you want to keep up to date and get notified when we release new videos, click on like and subscribe. This helps us keep the channel going and lets us know that you're enjoying our content. Imagine being introduced to a concept so powerful that it has roots in a variety of scientific fields, and has been utilized in numerous ways throughout history. A concept so phenomenal, it's often associated with disorder, randomness, or uncertainty. Welcome to the fascinating world of entropy and its connection to information. Let's take a stroll down memory lane to 1850, when Scottish scientist and engineer William Rankine first introduced the thermodynamic concept of entropy. He referred to it as a thermodynamic function or heat potential. But it was German physicist Rudolf Clausius, a trailblazer in the field of thermodynamics, who further defined entropy in 1865 as the ratio of an infinitesimal quantity of heat to instantaneous temperature. Clausius initially called it transformation content, or Verwandlungsinhalt in German, but he later chose the Greek word for transformation to coin the term entropy. He interpreted the term to mean disgregation and applied it to the structure of microscopic organisms. This concept of entropy is at the heart of the second law of thermodynamics, which states that for an isolated system left to spontaneous evolution, entropy cannot decrease over time. Isolated systems therefore move towards thermodynamic equilibrium, a state of maximum entropy. This law also highlights the irreversibility of certain processes. Fast forward to Austrian physicist Ludwig Boltzmann, who further refined the definition of entropy. He described it as the number of possible microscopic configurations or states of individual atoms and molecules of a system that agree with the macroscopic condition of the system. This led to the establishment of statistical mechanics, a new branch of thermodynamics that incorporates statistical disorder and probability distributions. The concept of entropy didn't stop there. In 1948, scientist Claude Shannon of Bell Laboratories introduced statistical concepts similar to measuring microscopic uncertainty and multiplicity to address the issue of random information losses in telecommunication signals. He named this missing information entropy, following John von Neumann's suggestion, and thus laid the groundwork for the field of information theory. So, entropy in its simplest form is a measure of disorder, randomness, or uncertainty. But as we'll see, it's not just about disorder. It's about possibilities. It's about information. Thermodynamics, the field where entropy was first identified, holds a crucial role in understanding this concept. Our journey through the intriguing world of entropy takes us to the heart of thermodynamics, a cornerstone of modern physics. Now, imagine a cup of hot coffee sitting on your desk. Over time, the coffee cools down, reaching the same temperature as the room. This is an example of an isolated system progressing towards thermodynamic equilibrium, a state that has the highest entropy. Entropy in the context of thermodynamics is a measure of this randomness or disorder. In the world of thermodynamics, the second law is a fundamental player. It states that the entropy of an isolated system, like our cup of coffee, cannot decrease over time. In other words, the system will always move towards a state of maximum disorder or randomness. This is why your coffee cools down and doesn't spontaneously heat back up. Here's another way to think about it. Imagine a box filled with gas molecules. Initially, all the molecules are on one side of the box. Over time, these molecules will spread out evenly throughout the box. This is a move towards higher entropy, a more disordered state. You'll never see the molecules spontaneously move back to one side of the box on their own. That would be a decrease in entropy, which, according to the second law of thermodynamics, is a no-go. The second law of thermodynamics is instrumental in our understanding of natural phenomena, from the cooling of a cup of coffee to the expansion of the universe. It's an unyielding law that dictates the direction of time's arrow, always pointing towards increasing disorder. It's fascinating, isn't it? This elusive concept of entropy, embedded in the very fabric of the universe, steering the course of everything from tiny gas molecules to vast galaxies. The second law of thermodynamics informs us that an isolated system's entropy cannot decrease over time, indicating a progression towards disorder. The concept of entropy takes a slightly different shape when we look at it through the lens of statistical mechanics. This is where Ludwig Boltzmann, an Austrian physicist, steps into our story. Boltzmann proposed a statistical perspective on entropy, offering a fresh insight into this elusive concept. He argued that entropy is not just about heat and energy, but also about the number of possible microscopic configurations or states of a system. Think of it like this. Imagine you have a box filled with red and blue marbles. If all the red marbles are on one side and all the blue marbles are on the other, we have an ordered, low entropy state. But if we shake the box and let the marbles scatter randomly, we end up with a disordered, high entropy state. There are so many more ways the marbles can be mixed than separated. This is Boltzmann's idea of entropy. It's all about the number of ways things can be arranged. Boltzmann's work didn't stop there, though. He went on to forge a connection between the macroscopic behavior of a system, what we can see and measure, and its microscopic interactions. Boltzmann discovered that the macroscopically observable behavior of a system, like the pressure and temperature of a gas, can be predicted from the average behavior of its microscopic components, the individual gas molecules. He expressed this relationship as a simple logarithmic law, which oscillates around an average configuration. This oscillation is governed by what we now call the Boltzmann constant, a proportionality constant that forms part of the modern international system of units. In essence, Boltzmann's work underlines the statistical nature of entropy. It's not just about energy dispersal or disorder, it's about the number of ways a system can be arranged and the probability of each arrangement. So, when we talk about entropy in the context of statistical mechanics, we're really talking about the multitude of possible states a system can take. It's a measure of potential, of possibility, and of probability. Boltzmann's work links the macroscopic behavior of a system to its microscopic interactions, offering a statistical perspective on entropy. Entropy exists not only in the physical world, but also in the realm of information. Let's shift our focus from the microscopic world of atoms and molecules to the world of telecommunication signals and data. In the mid-20th century, a brilliant scientist named Claude Shannon started to see a striking similarity between the concept of entropy in statistical mechanics and certain statistical properties of information. Shannon was working at Bell Laboratories, solving the problem of random losses in telecommunication signals. He realized that just as entropy in thermodynamics measures the degree of disorder or randomness, a similar concept could be applied to information. He proposed that entropy, in the context of information theory, could measure the missing information in telecommunication signals. Shannon's concept of entropy was revolutionary. He defined it as the average amount of information produced by a random source of data. The higher the entropy, the more uncertainty or randomness in the data. In other words, the more randomness there is in a set of data, the more information is missing. But what does missing information mean? Let's consider a simple example. Suppose we have a coin. If it's a fair coin, we don't know whether the next toss will result in heads or tails. The outcome is uncertain, and we're missing that information. Now, if it's a biased coin that always lands on heads, the next toss's outcome is certain. There's no missing information. Uncertainty and missing information increase together, and that's precisely what entropy measures. Shannon's concept of entropy was so similar to the concept in statistical mechanics that the great mathematician John von Neumann suggested he call it entropy too. So he did. Shannon's entropy became a cornerstone of information theory, a field that deals with quantifying, storing, and communicating information. In the context of information theory, entropy measures the uncertainty or the amount of missing information in a set of data. Now you might be wondering, how does entropy connect to information? Well, buckle up, because we're about to dive into this fascinating correlation. At its core, entropy is all about possibilities. In the physical world, it's about how many ways we can rearrange the atoms or molecules in a system without changing its overall state. But when it comes to information, entropy takes on a slightly different yet parallel meaning. Let's consider a signal that carries information. This could be anything from a text message to a radio broadcast. Just like in a physical system, the entropy of an information signal describes the number of ways its components, bits of data, can be arranged. More specifically, it measures the average uncertainty or surprise of a piece of data when it's received. So when we talk about the entropy of an information signal, we are essentially talking about its randomness or unpredictability. A message with high entropy is one with many possible states. It's unpredictable and therefore carries more information. On the other hand, a message with low entropy is predictable and carries less information. Let's take an example. Imagine you're sending a 5-letter message using the English alphabet. Theoretically, you could send over 11 million different messages. That's 26 to the power of 5. That's a lot of potential messages, most of which would be meaningless combinations of letters. But that's precisely what high entropy is, a vast number of possible states. Now here's the kicker. Not all messages are equally likely. Some letter combinations form meaningful words while others don't. So while the potential for high entropy exists, the real-world likelihood of certain combinations significantly reduces the actual entropy. This is where the connection between information and entropy really shines. Just as entropy in a physical system measures the disorder or number of possible states, the entropy in an information system measures the variety or unpredictability of data. So, there you have it. The connection between entropy and information isn't just a theoretical concept, it's a crucial principle that underpins the way we communicate and understand the world around us. Just as entropy measures the disorder in a physical system, it also measures the variety in an information system. Scene script. Let's make this a bit more tangible with some everyday examples. Imagine you're in a room and you spray a bottle of perfume. Initially, the scent is concentrated around you. Over time, the fragrance molecules disperse throughout the room until it's equally detectable in all corners. This is entropy in action, the perfume molecules spreading out from a state of order to a state of disorder. Consider a freshly shuffled deck of playing cards. When you first crack open a new deck, the cards are neatly ordered by suit and rank. But once you start shuffling, that order becomes disrupted. Each shuffle increases the disorder, the entropy of the card deck. No matter how many times you shuffle, you'll never return to the original, perfectly ordered state. This is an example of the second law of thermodynamics. Entropy always increases. Let's look at another familiar example. A hot cup of coffee in a cooler room. Initially, the coffee is hot and the room is cool, but over time the heat from the coffee disperses into the room and the coffee cools down. Eventually, the coffee and the room reach the same temperature. The heat is spread out, increasing the overall entropy of the system. Now let's think about a Rubik's Cube. When it's solved, it's in a state of low entropy. Everything is in order. But as soon as you start twisting and turning it, the cube becomes more and more disordered, increasing its entropy. The cube has many more disordered states than ordered ones, so it's far more likely to be in a state of high entropy. Finally, consider the process of cleaning and tidying a room. When you clean up, you're artificially reducing the room's entropy. But the moment you stop maintaining it, disorder starts creeping back in. Clothes get tossed around, dust settles, and before you know it, the room is a mess again. This is entropy, the natural tendency towards disorder. These examples illustrate how systems naturally evolve towards states of higher entropy or disorder. So, what have we learned about entropy? We've taken quite a journey, starting from its roots in thermodynamics, where entropy was first recognized as a measure of disorder or randomness. It was here that we discovered the second law of thermodynamics, which states that in an isolated system, entropy can never decrease over time. This law steers systems towards a state of maximum entropy, which is also the state of thermodynamic equilibrium. We then delved into the realm of statistical mechanics, where we found Ludwig Boltzmann's interpretation of entropy as the number of possible microscopic configurations of a system. This perspective gave us a statistical lens to view entropy, revealing it as a measure of disorder and probability distributions. We also learned about the Boltzmann constant, which forms a bridge between the microscopic and macroscopic worlds. Our journey then took us to the field of information theory, where entropy found a new home. Here we discovered that Claude Shannon had borrowed the term entropy to describe the loss of information in telecommunication signals. This perspective of entropy as missing information opened up a new way of understanding the concept. As we delved deeper, we uncovered the profound connection between information and entropy. We saw how a signal's information describes the variety of messages that can be sent, much like a gas's entropy describes the number of ways its atoms can be arranged. This relationship illustrated how entropy is not just about disorder, but also about diversity and the richness of possibilities. We wrapped up our journey with examples of entropy in everyday life, showing how this concept is not confined to the pages of a science textbook, but is a fundamental part of our world. Whether in a physical system or a data set, entropy remains a fundamental concept in understanding the world around us. It's the silent force driving systems towards disorder and diversity. And with that, we conclude our exploration of entropy, leaving with a greater understanding of this fascinating concept. If you want to keep up to date and get notified when we release new videos, click on like and subscribe. This helps us keep the channel going and lets us know that you're enjoying our content. Curious about how your computer stores and transmits information, such as the text you input or the images you gaze upon? Let's unravel the process. Fundamentally, your computer communicates in a binary language that uses ones and zeros. This binary code stands for every kind of data, whether it's a digit, an alphabet, or even a pixel in a picture. Imagine a two-letter sequence in the English language. In theory, we could utilize around 10 bits of binary code to differentiate between any two-letter sequence. But if we're aware that we're broadcasting a word, we only require nearly 7 bits. You may wonder why? The key is to comprehend patterns and frequencies. Reflect on the English language. Certain alphabets, like E, pop up a lot more than others, such as Z. Just the knowledge that a Z is present in a word considerably lessens the possibilities. This is why E in Morse code is a straightforward dot, while Z, which is less frequent, is depicted by a more intricate --. By keeping track of which alphabets are used sparingly, we can condense the data we're transmitting. This may seem insignificant, but when managing a substantial amount of data, this data compression could lead to substantial storage savings. It's a bit like playing Scrabble. Just as we acknowledge that most sequences of ones and zeros are inconsequential, we also recognize that not all Scrabble tile combinations will create a valid word. Occasionally, a random selection from the bag might lead to a significant sequence appearing on the board. The task is to differentiate these substantial sequences from random noise. Just like we would need to ascertain whether a seemingly arbitrary arrangement of ones and zeros on a disk drive is indeed housing valuable data, or just masquerading as noise. Isn't it how knowledge of what we're transmitting can aid in data compression and conserve storage capacity? Now, let's dive a little deeper into the world of data compression. One of the most fascinating aspects of data compression is how it leverages the frequency of information. Let's take the English language as an example. In English, some letters appear more frequently than others. For instance, the letter E is used more often than Z. Understanding this allows us to compress data more efficiently. Imagine a game of hangman. The moment a Z pops up, you're likely to guess the word more quickly because there are fewer words with Z. This principle applies to data compression too. We assign shorter codes to more commonly used data and longer codes to less frequent data. Consider Morse code. In Morse code, E is represented by a single dot, while Z is --. Why? Because E is more frequent, it gets a shorter, quicker code. Z, being less frequent, can afford to have a longer code. This principle is at the heart of data compression, but there's more to it. The complexity of a message also has a significant impact on data storage. A more complex message, one that's less predictable or more improbable, contains more information. Consequently, it requires more data for storage. For example, think about a Scrabble game. The sequence of letters in a well-played word is less probable, more unique, hence it's more informative. Conversely, a random sequence of tiles from the bag, even if it accidentally forms a word, is less informative because it's more probable, less unique. In the realm of computer science, a similar rule applies. A unique configuration of bits on a disk drive, one that's less likely to occur by chance, holds more information and thus requires more data for storage. So the more complex a message, the more data it requires. But what about random data? Randomness. It seems chaotic, but can it also hold meaningful information? Let's take a playful example of Scrabble, the classic board game we all know and love. Now imagine drawing tiles from that well-worn bag. Sometimes, purely by chance, the letters you draw can spell out a perfectly valid word. It's random, yet it holds meaning. Now let's take a leap from the board game to the realm of data storage. Consider the countless configurations of ones and zeros that make up the binary language of our digital world. Most combinations may seem like gibberish, but every now and then a random sequence might translate into something meaningful. A word, a command, even a piece of code. It's like finding a valid Scrabble word in a sea of scrambled tiles. But here's where it gets interesting. We humans, with our pattern-seeking brains, often tend to see meaning where there is none. We look at complex patterns, in the neurons firing in our brains, in the laws governing the physical universe, or even in the seemingly random ones and zeros on our hard drives, and assume they must represent something significant. We're wired to seek order in the chaos, to find signal in the noise. But what if some of these patterns are merely the result of randomness, like those accidental Scrabble words? What if, in our quest for meaning, we're sometimes just seeing the echoes of chance? It's a humbling thought, isn't it? Yet, it's not all existential crisis and philosophical quandary. This propensity to find meaning in randomness can also be a powerful tool. It allows us to see potential where others might see gibberish. It pushes us to dig deeper, to look closer, to question, and explore. So even in randomness, there's a potential for meaningful information, but how does this relate to entropy? Well, stick around. We're about to dive into the fascinating intersection of information, randomness, and entropy. It's a journey you won't want to miss. Information and entropy, two concepts that seem so different, yet share striking similarities. When we think of high-entropy systems, we imagine chaos, unpredictability, and randomness. Yet, these are the systems that hold the least amount of information. Why? Because they're unpredictable, we can't anticipate their next state, so we can't extract much information from them. Now, imagine a system that appears to be high entropy. It looks chaotic, random, but upon closer inspection, we find patterns, sequences, a hidden order. This is where the magic happens. This seemingly chaotic system can store a vast amount of data and information. The trick is in the examination, the willingness to delve into the chaos and find the underlying order. So, next time you look at your computer screen, remember there's a whole world of 1S and 0S working behind the scenes to bring you every bit of information. If you want to keep up to date and get notified when we release new videos, click on like and subscribe. This helps us keep the channel going and lets us know that you're enjoying our content. Ever wondered how black holes, the universe's ultimate memory banks, remember everything that falls into them? In 1974, Stephen Hawking made a groundbreaking discovery. He found that black holes, over time, fade into nothingness. This phenomenon is due to the continuous creation of particles and antiparticles in space, some of which are consumed by the black hole, while others escape, causing the black hole to glow faintly. Black holes, as defined by Einstein and Hawking, are categorized as classical and quantum, respectively. The differences between them are quite fascinating. Classical black holes, being eternal, don't really have an issue with knowing what's inside. What goes in, stays in. They are also defined by just 3 numbers. However, when we introduce quantum mechanics into the equation, things get a lot more interesting. Quantum black holes, unlike their classical counterparts, have a certain heat to them. They radiate and ultimately evaporate. This heat, a fundamental aspect of thermodynamics, allows the encoding of information. The entropy in black holes is immense. So immense that the surface of a single supermassive black hole, like the one at the center of our galaxy, has roughly the same amount of entropy as the entire visible universe at the beginning of time. Just imagine the vast amount of information that could be stored in all those potential microstates. However, it's still unclear how this information could be inscribed onto a black hole's surface. Interestingly, black holes emit radiation into space that over quadrillions of years should gradually dissipate, providing plenty of time to reassemble your robot friend from its remnants. While we await a theory of quantum gravity to fully understand the interactions between black holes and quantum mechanics, we can make some assumptions. According to Hawking, the radiation emitted by black holes during their evaporation would not be entirely random. Instead, the spectrum might contain tiny wiggles and bumps that, if interpreted correctly, could reveal what had fallen in. What's more, the idea that we, or at least our component atoms, might one day fall in, is intriguing. It's somewhat comforting to know that your essence could be quietly inscribed in a thin, icy lake of radiation. This suggests that we will continually be encoded into new forms that will exist indefinitely. In your next existence, you might be a sun, a moon, or even the very essence that sparks up a black hole. In conclusion, black holes are not just massive gravitational sinks. They are quantum, heat-emitting, information-encoding entities that might hold the key to understanding the universe's past, present, and future.